So last time where we stopped was complex Fourier series representation of a function which satisfies Dirichlet conditions, right? And we said that same as expressing a function in terms of sine and cosine. So I will get started with that. Let's start with complex Fourier series representation of a function So we know that f of t can be written as some complex Fourier coefficient Cn exponential of I 2 pi n over t, n going from negative infinity to plus infinity, where t is the period of this function. We had shown that the coefficient here C of n is a complex Fourier coefficient. It can be written in terms of an and bn's, which are the real Fourier coefficients for which we had developed the formula. Okay, so this is where we stopped last time, where Cn, this coefficient was given as what? 1 over t integration over one period. In this case, t is the, can put 0 to t or whatever it is, but minus t over 2 is fine. F of t exponential of negative I 2 pi n Alright. So this is how the Fourier coefficient is given. If you express it in terms of for the complex, we have to calculate only one coefficient, and of course Cn will be complex. Okay, but whatever you get it. All right. So I said I'll start from this to understand what is Fourier transform. Right. This is still a function which is periodic. Right. So if you want a representation for a function which is non-periodic, yet you want to write it in terms of sine and cosine, what would that look like? Okay, that is the Fourier transform. So this is a representation. So representation for a function which is non-periodic. That is one thing. I mean, that's what we seek to get a representation of a function which is non-periodic, and you want to write in terms of sine and cosine still, right? This is nothing but sine and cosine, right? Exponential is nothing but sine and cosine, which is and this is possible in an infinite domain. Okay, that's what we are going to say. That is possible, which is such a representation is possible in an infinite domain, and also we have to satisfy the condition that square modulus of the function is finite. So just as we had Dirichlet condition for a complex Fourier series to exist, for the Fourier transform to exist, we have to satisfy this condition, f of square modulus of the function. F could be complex function, right? I mean, the way we've written. So square modulus of the function integrated over infinite domain must converge. Okay, so if this condition is satisfied, then we can give a Fourier transform representation of a function, of a non-periodic function in terms of sine and cosine in an infinite domain. So that's another word I'm going to add. Okay, so this is an important word, that's an important word here, and this condition has to be satisfied. All right, so all we know is the function is non-periodic. So from what we know, if you have to proceed from this, what did we say? If you have to use a complex Fourier series representation to represent a function which is not periodic, what is the first step that you will do? That's what is going to lead to the definition of Fourier transform. I'm just leading you to the definition of Fourier transform. Function is not periodic. What is it that is representing periodicity in this definition of complex Fourier series?
2 pi n. I didn't get the question.
So what the question is, how what I have written is for a function which is periodic. What is the periodicity of this function here?
Oh, sine 2 pi n.
No, t is the t, 2 pi n, whatever x or L. L is
2 pi is the.
Yeah, so no, that is not the, it is this the periodicity, right? Like cosine 2 pi n x
Right.
over L. So t is your periodicity of the function in this case. Now, if the function is not periodic, what should I do to this thing to get an expression? First step, I mean, that's the key steps that you have to understand in going from Fourier series to Fourier transform. We are going, this is still Fourier series, right? So how to transition from Fourier series to Fourier transform, right? That's what we are. That will give us the representation for non-periodic function. So the key word here is non-periodic. Here it is periodic. And I want to go from what I know to give a new representation for complex, for this non-periodic function.
Make the period infinite. Make the period infinite.
The period, it is not repeating itself. That means the period is infinity. So the first step is, I'll set t go to infinity. The periodicity has to go to infinity, right? That means it's not repeating its, at okay, so that is the first step, okay? All right, so if I make the periodicity, so I'm going to start with what you know to get the representation. Okay, just let me call this quantity 2 pi n over t as something omega n. Okay. And so we have, so let's say this is some frequency, right? Angular frequency thing. All right. So what we have is how these frequencies are arranged. Let me just call it delta omega n. There's nothing but 2 pi over t. I've done nothing but just writing this as omega n at this point. All right. Now, if t goes to infinity, what is it? What are the few things that you can see could be happening on this expression of the complex Fourier series? I'm also going to write f of t is nothing but I can substitute for Cn as a first step. All I've done is just substituted sorry, f of t, I have, okay, minus t1, okay. All I have done is substitute for Cn in this expression at this point. I still have all this. So t tending to infinity, what all should I do? What is it that is at least very obvious to you? I mean, the limits will change, right? I mean, that's obvious, right? T goes to infinity, that is changed. Now, I'm going to also write this 1 over t as 2 pi over delta n, and as t goes to infinity, what happens is this variable omega is not anymore discrete. They come closer and closer, so it becomes a continuous spectrum. The frequency spectrum becomes continuous. So that's what happens. So I'm going to write this 1 over t here as based on this. So as t tending to infinity, I can write 1 over t as this, as t tends to infinity. It is no longer discrete spectrum. It becomes closer and closer because t is infinity, so delta omega n is going to 0, so that means it's a continuous spectrum. The frequency spectrum becomes continuous. All right. So I'm going to replace this quantity as, first of all, let me first maybe step by step so that you understand it. Here it was 2 pi over delta. 1 over t is delta omega n over 2 pi. Okay? And at this point, it's still like this, so that you understand what I'm going to be doing. I've done nothing but just, substitute for this at this point. And now I'm going to make t go to infinity, that is non-periodic function. Periodicity goes to infinity. So my function, now I'm writing the function representation for a non-periodic function. Okay. So this will become, summation will become integration too, right? So this will become minus infinity to plus infinity, and this will become dw d omega over 2 pi. Okay, and this becomes minus infinity to plus infinity f of t prime. Okay, and this one whole thing is becoming minus I omega t prime, because that has become, omega n has become continuous, so it has to be replaced by that, dt prime, and this one is nothing but I w t. Okay, so this has become also continuous. Frequency spectrum has become continuous. So this, we don't no longer call it omega n or w1 w2. It's a continuous spectrum. So what we have done is nothing. Oh, this omega, right? Yeah, okay, good. So what I've written is then this function f of t as 1/2 pi of. Okay, we can decide what to. We have to put 2 pi in one or the other. I'm going to emphasize that definition a little bit more. I will write this expression like this: minus infinity to plus infinity of dw, and whatever is the quantity inside is what I'm going to call as Fourier transform of the function. Okay, and I have exponential of I omega t, and this is f of t. This quantity is called as Fourier transform of the function. So the way I have written right now is the following: f tilde omega is then, in this definition, is minus infinity to plus infinity f of what is that? Exponential of minus omega t prime dt prime or dt. So there we go here. Okay, so this is called as Fourier transform, and this is the inverse of the Fourier transform, okay, of the function. So inverse for transform would be f of t can also be written as then, in this case, I'm writing it as 1/2 pi minus infinity to plus infinity of, oh, I've already written that, okay, it's there. Okay. So where to observe this factor 1/2 pi is arbitrary in some sense. You have to be consistent. Once you start a definition, you have to be consistent for a given problem, because in many books what they will do is, you don't have to remember, okay, I have to have 1/2 pi factor in this inverse Fourier transform and nothing in here. So most people in many books, they will distribute this equally. Okay, so there's nothing stopping you, because I can put this 1/2 pi here and 1/2 pi here, so you have a very symmetric expression for Fourier transform and the inverse transform of that. Okay, so you will, if you see that, that's what they are doing. Okay, but for the moment I'm going to keep this, and I'll tell you why I'm keeping that for the definition of Dirac delta function. And then, but in general, for any other function, you will distribute these things equally. The weight factor, it's a multiplication factor, right? I mean, so nobody says, why, this is it. I can put this 1/2 pi here, and I can have 1/2 pi here. So in the definition of f of t, I could have had like this, where f tilde is like that. Okay, so it is up to the user in a given problem. If you are asked to do something, you just be consistent to calculate the Fourier transform and the inverse Fourier transform. Okay, so you will see this all the time in books, and some books will use one convention, other books will use another convention. So don't even worry about it. It's just a multiplication factor, okay, that you have to take care of. Is this clear? Okay. All right. All right. So this is called as Fourier transform of a function f of t. All right. And so any function which is in t space, if it's not periodic, you can write it in this form. Okay, so we have 1/2 pi into whatever this integral in here. You have to calculate both these quantities. All right. Now I want to One of the reasons I'm doing this is to introduce you to the definition of Dirac delta function. Okay. Okay, we got this. Let me just proceed from here. All these things. Right down here, because this is a really compact notation. But so I have, let us say, 1 over 2 pi I wrote, right? D omega of, supposing I had written it like this, minus infinity to right? Okay, so that's what we got from the complex Fourier series. All right, so if I go back to this definition, if I look at this, and I'll invert the order of integration. I can always do that. Okay, I mean, whenever you have double integration, you can always play with all these things. Invert the order of integration. All right. So here was T was doing, and then this thing. But if I want to reverse the order, what happens to f of t? F of t is nothing but 1 over 2 pi, and I want to do dt prime, I want to do later, let us say, then I have f of t prime in this case, right? Also here, then I do have this quantity minus infinity to plus infinity of d omega exponential of I omega t minus t prime is something like this. All right. All I've done is, I got two. One is integration over t prime, the other one is over omega, and I decided to reverse the order of integration. Okay. So what do I have in the left hand side? We have to have left hand side equal to right hand side. I mean, this has to be satisfied. This condition has to be satisfied. How can I make left hand side equal to right hand side with all these double integration? Okay, I did that. I'm going to do the omega integration first, right? And so this will be something function of t prime, right? I mean, tt prime, and then you integrate it. So, and this integration over t prime. So whatever left over is a function of t. Okay, so that much is clear from the way the integration is going on. Now, how can I make left hand side equal to right hand side?
Means the direct delta function.
Which one?
Delta of x t minus.
So what should be Dirac delta function? I mean,
Delta of t minus t.
no, is it
2 pi t.
the whole integration?
Yeah.
So I get a definition of the Dirac delta function. So what I'm going to say is, this has to be, condition has to be satisfied. Then I'm going to give a definition of Dirac delta function as delta of
1 upon 2.
t minus t prime, okay, is nothing but 1 over 2 pi of minus infinity to plus infinity of this quantity. Okay. So literally I put this 1 over 2 pi, then I have f of t is nothing but minus infinity to plus infinity of Dirac delta function f of t prime dt prime. Okay. And this exists only for t equal to t prime, and otherwise it's all 0, so this has to be f of t. This is what used in the Green's function definition. Remember the other day one of the L of g equal to whatever we had to prove. But this, that comes from here actually in some sense, because it comes from the Fourier transform theory, that all that comes from the Fourier transform theory. We have this, and so that means I have a definition for the Dirac delta function, okay? This is the fundamental definition of Dirac delta function in some sense, right? I mean, in the Fourier transform represented Dirac delta function. What do you know about Dirac delta function in the T space?
Is that t? If
So-
t equal to t dash, it's equal to b equal.
Just a minute, let me write down. So this is definition of Dirac delta function. Okay, we know about the left-hand side, right? How does that function look like?
If t equal to t dash is equals. Means what?
Sharp pick up.
Yeah.
It is sharply peaked. It goes to infinity, okay, and everywhere else it's 0. So in T space, that's what we know. This function behaves like that. Now, what have we written? The right-hand side is what?
In t dash.
No. What is the physical meaning? I'm just trying. We are here. We are saying Dirac delta function. You know, here. If you plot that for t equal to t prime, it's going to be like that, and everywhere else it is going to be 0, right? I mean,
Yeah.
okay, t equal to t prime, it is going to peak, and everywhere else is going to be 0. That is a functional form of that. But what have we expressed that as?
Sine and cosine form.
Sin-
In terms of the means that
Yeah, so we have written in terms of sine. This Dirac delta function is sharply peaked. We have written it in terms of harmonic waves of all frequencies from omega equal to minus infinity
to plus infinity.
plus infinity. Okay, so and these sine and cosine phase are they have same amplitude, and they are in phase at t equal to t prime. Okay, so what I'm going to lead to the other definition. Something which is peaked in one space is really uniformly distributed in the omega space, because that is also coming from there. I mean, so you have represented a function which is sharply peaked in terms of, you know, sine and cosine, you know, because that is nothing but sine omega t plus I sine omega t, where omega has all frequencies, the infinite domain. So that's what it is happening. You are something, you know, it's a very different representation. Okay, how does it converge? You know, you have so many harmonic waves, and that represents this function in the other space, dual space, D space. Okay, so that is also the meaning of this. Okay, so meaning of this is nothing but it's a superposition of Dirac delta function is nothing but superposition of sine and cosine waves or harmonic waves. You want sine and cosine waves of all frequencies. Okay, because it is minus omega plus infinity, right? Of all frequency, and these are these waves are in phase at t equal to t prime. Okay, their amplitudes are same, and they are in phase for it to peak at t equal to t prime. Okay, so that's the physical meaning of this representation if you look at it. And so we'll talk about that a little bit further also. All right. So let us keep this definition of the Dirac delta function for a moment. I'm going to write down all that also maybe. Let's keep this. So to integrate over omega. Okay, it's already done. Okay. So that's the definition of Dirac delta function. Integral representation of Dirac delta function, or Fourier transform representation of Dirac delta function. That is it. All right. We call this as the first one of the representations. So, so I'm going to consider, I'll write down the definition a little bit later after doing the problem. We are going to have, consider uniform distribution, okay? At this point, it's finite width. Let's say the height of this is 1, okay? So I am having distribution in omega space like this of some function, which has unit, it's constant in this domain minus omega to plus omega. And I'm going to take the Fourier transform of this in the other space and see what happens to it. Okay. So this will lead me to another definition of Dirac, another representation of the Dirac delta function. That's what I'm trying to do. If this is the case, f of t, okay, I'm going from omega to t space at this point, okay? So f of t is nothing but if I want to distribute equally, I'm starting with a very general definition of going from Fourier transform to inverse Fourier transform. Then I'm going to write it like this, minus, I'm taking the factor here, it's 1 over square root of 2 pi, f tilde omega, exponential of I omega t. I have to integrate to omega because this function here on the right hand side is t, right? So if I want to go from this omega space to see what is the function, okay, the inverse Fourier transform, whatever you want to call it, the other, the function represented in the other space, the dual space, t space. Since this is equal to 1 in this space, this looks like nothing but 1 over square root of 2 pi minus omega to plus omega of exponential of pi omega t d omega, right? Because everywhere else it is 0. It is 0 elsewhere. So this function f tilde omega is 1 in this domain minus omega less than omega is equal to 0 elsewhere. Okay. So this looks like a function like this. I omega t, since the integration is called omega, I have I t in the denominator minus omega to plus omega. Or f of t looks like 1 over square root of 2 pi 1 over it exponential of I omega t minus exponential minus omega t. Alright? Is okay? Alright. Now, what is this quantity? 2 sine omega t, cosine plus I sine, cosine minus I sine. So it is 2i, right?
2i sine.
Yeah. So it is 1 over square root of 2 pi, 1 over it, and this is nothing but 2i sine of omega t. Alright, I and I will cancel. So f of t looks like nothing but square root of 2 over pi, it looks like, is that right? Sine of omega t over t. This is how it looks like at this point. Now I'm going to multiply and divide by omega. Okay. I can do that. Okay. So this is my original function, which is it is uniform, and I take the inverse transform of that in the t space, and that is what it has become, right? Now, so we know this function. Two things I'm going to do. I'm going to make this distribution uniform to infinite domain. I started with a minus omega to plus omega, but if this is a constant everywhere, okay, so I'm going to let the width of this distribution to infinity, okay, and it is constant everywhere, and see what happens to it. So this function I'm going to examine in the limit omega tending to infinity, that is the width of the distribution has gone to infinity. Alright, so if you plot that function, how does it look like? At omega equal to 0, what happens? Or t, omega t equal to 0, t, how does it look like? F of t, if I want to plot f of t as a function of t, so this is f tilde omega, okay? So if f tilde, so the other space, the Fourier space, how does this function look? F of t as a function of t. So this is how this distribution looks. I'll also put omega tending to infinity, but t equal to 0, what happens? Because I want to see how this function looks like.
It's a constant.
What is the value of the constant?
The root 2 pi by omega.
So sine x over x, limit x equal to 0 is 1, right? So this function is nothing but at t equal to 0, it has a value square root of 2 over pi times omega, right? And
Omega tends to infinity.
so it is something like this, okay? And then what happens? There are some waves here, and this is equal to what? At t equal to pi omega, t is equal to pi over omega, right? The first node will be there. So what happens when omega tends to infinity?
Only peak at 0.
So this peak has become infinity, it goes to infinity, and this one keeps on shrinking, right? So this will start resembling like a delta function when omega tends to infinity, because this peak is going to go up, and this is going to come closer. So this sort of corresponds to, in the limit omega, so now let's look at limit omega tending to infinity. It seems to be having features of the Dirac delta function, right? Because of the way this function behaves. Okay. Now, but there's our definition. The only trouble here is when I started this definition, I had put 1 over square root of 2 pi in f to in going from f to, whereas Dirac delta function has already the entire thing thrown in as 1 over 2 pi. So I need to have the following. So this function that I had, of uniform distribution, is nothing but square root of 2 pi term Dirac delta function should correspond to limit omega tending to infinity of square root of 2 over pi of, now I can get rid of my omega because I don't need that anymore. Sine of omega t, omega will cancel this, or I have Dirac delta function is square root of 2 can also cancel, so I have sine of omega t over pi t limit omega tending to infinity. So in some of the quantum mechanics books you will see Dirac delta function also written this way. Okay, I mean, although this is sort of very common, but you will see it also in this form. Okay, so you have to recognize that as if it occurs, you have to as a Dirac delta function. Yeah.
That is t equal to 0.
What did you say?
No.
Huh? I put the pi here. Pi is coming. Square root of pi, square root
No,
of pi.
that limit. Omega tends to 0.
Omega tends to, no, width is becoming infinity.
So that's the second.
Oh, second one. Yeah, of course. Here it is. Yeah. The width has to. So this is of course omega tending to infinity. Yeah. So what it is if you have a uniform distribution in the infinite domain, it looks like a sharply peaked function in the t space. Okay, so that is a duality that is interesting. With going from one space to other, and in many problems, you will solve a problem in real space or K space to simplify. Okay, I mean whatever is easier. Okay, I mean so you will always go between one space to other depending on the nature of the problem, where you want, how you want to solve it. Okay, that's very common. K space with got periodicity, you will do K space, but you can always do the problem in real space too. They are all equivalent. In one case, maybe it looks more complicated, but then maybe simpler. Okay, so this is something that you have to know because you will come across this definition of Dirac delta function, and this might be not so much, maybe somewhere you'll see in scattering theory or something, but that one definitely you should know because it will help you to solve a multiple, if you have a multiple double integration, triple integration, it'll immediately, once you can identify something like that is coming, you will reverse the order of integration to see if there's a Dirac delta function when you have multiple integration, then it will immediately simplify your double integration to a single integration and all that. So okay, now that you know this, let me just say a few more things. Okay, some properties of Dirac delta function. So delta t is of course nothing but 1 over 2 pi of minus infinity to plus infinity exponential of I omega t d omega. All right. Complex conjugate of that is this. There, right? And delta of minus t is also what? 1 over 2 pi minus infinity to plus infinity of exponential of I omega t d omega. Right? I'm just minus t, I just put it. So I have complex conjugate of Dirac delta function is same as delta of minus t. All right. Now, delta of minus t, how does it behave? How is it different from delta of t? We know that the function delta of t is sharply peaked at t equal to 0, 0 elsewhere. What about delta of minus t? T equal to 0, doesn't matter. So delta of minus t is exactly equal to delta of t. So I can, because of the nature of Dirac delta function, so I can really write Dirac delta function. So this means, what we have is delta of minus t is same as, because it's 0 elsewhere, you understand, but at t equal to 0 it has to be infinity. So we have this property, delta of minus t is same as Dirac delta of positive t. So I can equally write Dirac delta function definition as 1 over 2 pi minus infinity to plus infinity exponential of negative I omega t d omega. Okay, so don't fret about do I have to have plus or minus, because if it is Dirac delta t, it is exactly the same. Okay, so because of this property, it is also, so they are the same. Okay, so both definitions are the same. So that is something I want you to be keeping in mind, and it's all because of the Dirac delta function, the way it behaves. Okay. Now, what is Fourier transform of Dirac delta function? All right, without calculating first, okay? What do you think you expect it to be?
Means the e power goes to 0.
Are you asking for the interval?
I'm just going to say, of course we'll do it exactly, apply the definition, and we're going to do it, right? I mean, but I want you to even first guess the solution, roughly at least, okay? I mean, what it should be.
It's going to be switched.
Huh?
Switched.
What is switched? I just said something about T space and omega space. That is what you have
It's
to
a square.
If something is sharply peaked in one space,
My guess is a single point.
it's a constant. It is spread.
It's a
It's a
square.
constant value. Okay, that's what we did with the unit representation. You understand? It's a distribution is constant in omega space. It was one everywhere. Then it was peaking. Okay, it looked like so it should, whatever we do, we should we should get that kind of a result. Okay, and applying the actual definition now. Okay, so I just want you to first have that concept fixed in your mind and before we do the mathematical, integration and all that stuff. Okay, so that's because that's the most critical thing to understand always. Okay, I mean, all right. So delta, if I'm just Fourier transform definition I'm going to apply, right? So I'm going to distribute this 1 over 2 pi. I'm just considering as any function, okay? Just for minus infinity to plus infinity, exponential of I omega t. This is what I will do, right? Even for calculating, going from one to the other, this is the definition I will use, okay? All right, and I have the definition of Dirac delta function written on the board, so I can write this as 1 over square root of 2 pi of minus infinity to plus infinity exponential of I omega t delta t, and delta t is nothing but 1 over 2 pi of minus infinity to plus infinity of exponential of minus omega prime t d omega. Omega is a dummy variable, so I made it omega prime because I already have omega here, so I'm just going to be careful. Okay, I've done nothing, I've just used the definition of Fourier transform. Okay, giving a function, you can, that is the definition of Fourier transform, okay, for any function. So I'm using delta t as a function, and if that is the definition we got it, then I 1 over 2 pi there. All right, so as usual, I got double integration. So I'm going to do order of integration, reverse the order of integration, okay, of t and omega. So that is always what you have to do when you have something like this. Reverse the order of integration. So I'm going to do omega first, and then t. Okay, so 1 over root 2 pi of minus infinity to plus infinity. Let's keep. We'll decide where to put this. D omega prime. Let it be there, and there's nothing else I can do, but I have to take maybe this 1 over 2 pi inside of minus infinity to plus infinity of exponential of, one of them is plus, is it? That is delta, I can take a plus, doesn't matter, I'm going to take a plus. Delta t can be plus or minus, but I'm going to take this definition at this point, okay, because I have that. So exponential of I okay, omega prime minus omega of t, and I have dt. So what is this function now? What is this one?
Two sine.
What did you say?
Sine and cosine?
Yeah.
No, but this integration. It's same as, it's Dirac delta function. It is, that's what I want you to remember, that when you have 1 over 2 pi infinite domain, previously it was on the t space, but it's the other way around. So this is also Dirac delta function, but omega prime minus omega. That's what it is, okay? So this integration, so I'm always doing the double integration to reduce one to find if there's a Dirac delta function somewhere. So this one, integrate over t, you're left with Dirac delta function of omega prime minus omega. That's what you're left with, okay? So, and then, so this becomes then nothing but 1 over square root of 2 pi of minus infinity to plus infinity of d omega prime which is equal to what?
1.
That's equal to 1. So this is nothing but 1 over square root of 2 pi. Okay. It's a constant. Okay, that's all. I'm just trying to show you we had done it before in a different way, but I'm just using that definition to get back what we are trying to do. Okay. All right. Is this okay? Okay. So I think you should have this, these two definitions you should really remember. I mean, it will help you a lot to simplify your multiple integrations. Okay, let me talk about one more thing. Okay. Just as we had, Fourier series is a combination of sine and cosine series, but if a function is odd, we had only Fourier sine series, and if it's even, we had only Fourier cosine series. So similarly, we have Fourier sine and cosine transforms. Okay, so I'm going to so if a function is odd, okay, then we know f of minus t is negative of f of t. Okay, that is something that we know. In this case, one can define a Fourier sine series. It will be, I put S to represent it's a sine series, and the definition of that is given as square root of 2 over pi. And I'll prove this to you where it comes from. 0 to infinity of f of t sine of omega t dt. Okay. So two things have changed. It's not 1 over square root of 2 pi, this is this. Limits are not minus infinity to plus infinity, 0 to infinity. So that has also changed. The advantage of this is, when I have to write f of t, if you can identify, then it is simply, I don't have to change the sign, plus minus kind of a thing, 0 to infinity, f s tilde omega sine omega t. This is now integration over omega. Okay. So when you go from this is a Fourier transform and this is inverse Fourier transform, you can go back and forth, and you don't have to put in one case minus omega t, in the case I plus I omega t. And similarly for even function, you can see it's cosine function. This will be f of t cosine omega t. The normalization factor remains the same. Okay, and you can go back and forth easily from one space to the other space, t space to omega space, without worrying about where I have minus all that also. Okay, so let me write down before I forget. If f of t is even, of course f of negative t is this, and in that case we define Fourier cosine. This represents cosine series. Okay, and it is simply square root of 2 over pi 0 to infinity of f of t cosine of omega t dt. Okay, and similarly the inverse one will be the other way around, so you don't have to worry about that. this clear? Okay, so now where does it come from, these definitions? Okay, we can prove that from what we know again. So I'll just quickly do it for only one case, sine series. You can repeat it for cosine series. All right, so, okay, what we know is the definition of Fourier transform, right? Let's go from there. So Fourier transform of the function f of t, I can write as 1 over square root of 2 pi minus infinity to plus infinity of f of t exponential of I minus I omega t integration over time domain, because I have omega here, right? This I can write, okay? This is the definition of Fourier transform. Now, this I can write as sine and cosine, right? And I know f of t is odd, okay? If f of t is odd, this is odd, when will this function survive? This integral survive? It's infinite domain. Exponential I omega t has sine and cosine, right? If I have cosine, that's an even function, odd function, and integration over infinite domain, that will go to 0. The only term which is going to survive is sine term. Okay, so cosine minus, this is what cosine, I have a minus sign, so cosine of omega t minus I sine omega t. So this integral I can write as 1 over square root of 2 pi. Okay, the term that is going to survive is minus infinity to plus infinity f of t. I got a minus I because of that sine of omega t dt. Okay, that is the only term that's going to survive. And this is odd, that is odd, becomes an even. The product of these two becomes an even function now, right? So I can write this as 2 times 0 to infinity. I can do that also. So this integral will become minus 2i over square root of 2 pi. Now 0 to infinity is coming because of that. F of t sine of omega t dt. I had to prove that, okay? I have square root of 2 pi, that's fine, but I had got the I sitting here, which is not negative I. We don't have that in the definition, so we have to do more tricks. Doesn't stop here. Okay, let me just write down this as now minus 2 over square root of pi, because you already know where the 2 factor comes from. So minus I square root of 2 over pi, okay? All right. So one of the things that we have to recognize is, if this is true, I also have f tilde of negative omega is also negative of f tilde omega. Okay, that is, in the other space, the function is odd also. Okay, so that is something you have to know. If this is the case, all right, so let me just now write down, I have got f of t here. So in all these cases, like a Russian doll, we have to keep on doing that. F of t is nothing but 1 over square root of 2 pi negative infinity to plus infinity, f tilde I omega t d omega. So by the way, I put the tilde sign for Fourier transform. I mean, the other one I don't. Okay, so that way we can keep track of whether it's where I put negative and positive sign. And I said this is true. F tilde minus omega is equal to. It's also odd. Okay, this is also odd in omega. If that is the case, what happens is this is nothing but again the same thing. Except I will have plus this time, 2I square root of 2 pi, 0 to infinity of f tilde omega sine omega t d omega. Okay, so that's this term that survives. The other one will go, and because it's odd times odd is even, I made the change the limits of integration also. So f of t is that. All right. Now, what I'm going to do is, I got f tilde omega here. I'm going to substitute what I have. So I get an expression for f of t, which is f of t is nothing but 2I square s minus 1 plus, so 2 over pi, I have 2 over pi. I'm substitute for this from there, okay? 0 to infinity of sine omega t d omega is there, okay, and then I have 0 to infinity of this guy for f tilde omega, which is f of t sine of omega t dt. All right, so just as we had written a definition for Fourier transform from scratch, I have this expression. Now I'm going to distribute this 2 pi equally here and there. And so what I have is the definition of Fourier sine transform, or Fourier transform in this case, which will be the square root of 2 pi. I'm going to write this 0 to infinity. I can write it like this, right? Sine of, nothing here much, nothing fancy, d omega. I'm going to call this times square root of 2 pi s Fourier sine omega, and then sine omega t is also there. Okay, sine, maybe I can write it. Okay. So this is the quantity with the, I'm going to distribute this equally, square root of 2 pi, okay, which I have, and call this as Fourier sine transform. Okay, so this is sort of this S, it's a function, but it's only, only the sine transform is given by this expression. The other way around, as I said, right? I mean, their fs tilde omega is nothing but that. Coming by from here, square root of 2 over pi of 0 to infinity of f of t sine omega t dt. Okay, this is t. There is this integration over omega. Okay, so both have to be there. So if a function f of t is odd, you can write give this representation where fs, this is the inverse of the Fourier transform, and the Fourier transform is given by that. But it's a very symmetric function, so that's why it's nice, because I don't have to worry about, where normally in the Fourier transform you have expression of minus omega t if it is not an even or odd. I want to say one last thing, which is an important thing, okay? Almost all functions, if it is sharply peaked, it is extended in other space, except Gaussian functions. So I want to mention that, okay? I mean, it doesn't change the shape of the function. That's the only case. A Gaussian function in real space and the Fourier space, let us say time space and omega space, or x space and p space, a Gaussian remains a Gaussian except the width of the Gaussian changes. This you'll learn in quantum mechanics, the Gaussian wave packet. And this is what leads to the Heisenberg uncertainty principle in some. There's no proof of otherwise the Heisenberg uncertainty principle. It is how the Gaussian wave packet behaves in x space and p space, or t space and omega space, because the Gaussian remains a Gaussian. You go through the whole thing, and a Gaussian wave packet will remain a Gaussian. And that because but the only thing difference is the distribution, how they are related leads to the Heisenberg uncertainty. I'm not going to prove it, but I just want to give you an idea of this because I think it is, important, at least in quantum mechanics. So I just want to mention this. Okay, how it looks like. All right. All right, a Gaussian, if you have forgotten, looks like this, Gaussian distribution. Okay, the sigma is the width of the distribution, right? I mean, in this case, x peaked around x equal to 0, so it is some distribution which is peaked around x equal to 0. In many cases, you have x minus mu whole square or something, relatively speaking. Okay. So, so what I'm going to show, this you can prove. Supposing I have a function like this. Okay. So, so this is a Gaussian, and the width of the distribution is tau. Okay. F of t. May have the width of this distribution or variance sigma, right? I mean, is nothing but tau. When you take f, the Fourier transform of this function using the definition, it becomes 1 over square root of 2 pi exponential of minus half. Tau now goes to the numerator and omega square. Okay. So here, this is the width of the distribution. In the other case, so basically the shape remains the same. The width maybe it's broader or something. Okay. I mean, so the tau has, in one case, the tau is small. If it is because of the denominator, it's 1 over tau. So the width of the distribution delta t, if it is tau, the width of the distribution in the omega space is 1 over tau, okay? So because of that, what you have is this condition, the distribution of the Gaussian packet in the, how it spreads in the t space and omega space, if the product is 1, okay? So if I put h cross, okay, then you have delta t times E is h cross omega is equal to h cross, okay? So it is how the Gaussian wave packet behaves in the two space. It could be x space, the dual space x, position and momentum space, or energy and tau space, is actually coming out of the Fourier transform theory. So in a way, Fourier transform theory has some implications in quantum mechanics in terms of, Heisenberg uncertainty principle. You know that if something is localized in x space, there's uncertainty in the momentum space, right? I mean, if you can locate the particle exactly, in x space, real space, you don't know anything about the momentum. So that's coming out of how the Gaussian function behaves in the two spaces, what the two conjugate spaces, and it is the width of the distribution of this Gaussian packet, is sort of the underpinning of the Heisenberg uncertainty. Because otherwise you cannot prove that, right? There's no otherwise proof of Heisenberg uncertainty principle. So it is there. So I want you to understand why Fourier transform theory plays a role, big role in quantum mechanics. It will be coming, Dirac delta function and several things. We'll talk about, I think, the foundation of quantum mechanics, a lot of things about Gaussian wave packet, why they emphasize about that. You'll learn about it actually. Yeah. Okay, I'll stop here.